Actually, I noticed in the chat the word happy birthdays for Jorge García Rojas and perhaps also for Javier Alcolea. So I think it's a good day for you guys. So happy birthday. There's nothing better than celebrating with your colleagues. So, okay, Martin, you're ready. Your presentation is up. So
I hope so.
You can go ahead.
Okay, thank you very much. Well, I'm going to be presenting this work, tomographic investigation of the jet in the NGC 2392, the planetary nebula previously known as the Eskimo Nebula, but now this name is considered to be respectful, so maybe we should try to change to the Lion's Head Nebula for this one. I'm not going to say that this is a unique planetary nebulae, but it's very peculiar. It was the very first PM where we discovered a fast outflow. There were some claims a few months before of a fast outflow in CRL 618, but then G.C. King and collaborators look at the longest shell spectrum of this PM, and they found very high outflows that they define as a jet-like multi-node bipolar mass flow with a velocity of around 200 kilometers per second and a small angle of collimation. So in a sense, NGC 2392 was the PM where everything started as for asymmetric planetary nebula. Let's see. Okay. Also, I would say that indeed is unique as for the expansion velocity of the inner shell, which is very fast. It's almost reaching 90 kilometers per second, which is unusual for ellipsoidal shells. It's not for bipolar planetary nebula, but it is for those that they have round or elliptical morphology. And something which is interesting is that this shell is expanding along a position angle which is different to that of the jet. So they are misaligned. Then as for the central star of this PM, well, it's actually a very wimpy central star. It does not have the UV flux with the effective temperature of 45,000 Kelvin to produce all the helium-2 emission that we see there. This is going to have a much higher substrate temperature, which is clearly discrepant with the temperature that we derive from non-LT models. And then the wind speed is about 300 kilometers per second, but this is not enough to produce the X-ray emitting plasma inside the hot bubble. It has a temperature of 2.2 million Kelvin. So basically the X-ray temperature that we see is about 1.5 times higher than the fast stellar wind can produce. In addition, this central star has the hardest X-ray emission from any central star of PM, peaking at about 1 kV and with a hard energy tail which extends up to 3 kilo electron volt. This is completely amazing for planetary nebulae. So many people have considered that there is a binary system there with a hot white dwarf, which actually would be producing the stellar wind and the UV flux to explain all the properties of the PM. And recently, Danekar confirmed this by finding a spectroscopic period of 1.9 days. Actually, there are discrepant periods, because if we look at the period from the nitrogen 4 line, which is considered to be rotational, it's about 3 hours, and we ourselves found an X-ray modulation of 6.2 hours in this source. So let's go back to the kinematics. This is a position velocity map along the 70 degrees, so along the jet, and we see that the jet actually seems to extend down to the central star of the PM. And also we see that there is a break in the velocity of the jet as this gets out of the inner shell, so it speeds up. It was Brent Lisowski who first indicated that that was really an active jet in a post-common envelope of PN. So the jet is still emerging from the central star. It would be nice to have an image of the jet, but the problem is that it's too faint compared to the bright nebular emission. So if you look here in this nitrogen 2 image, so you are able to see the jet here in the kinematical information, but when you look at the image, you don't see the jet. So some people have gone through kinematical data to try to find the jet. Bruce and collaborators in 1987, they used 25 slits crisscrossing the PN to produce a map of the velocities that they interpolated to produce isovelocity channels of this. And actually, when you go to the highest velocity channels, you find evidence of this emission from the jet. But actually, the morphological description is not very well. More recently, Maria Teresa also used this same technique with a lot of long slit shell data crossing the nebula and also along the jet to produce a 3D model of the nebula. Indeed, the model that they produced at that time was very comprehensive for all the different properties of those souls. So the problem with this kind of observation is that you have slits that they are apart a few arc seconds in some cases, and you need to interpolate the data. Data are obtained at different times, and so maybe the calibration is not the same. So it's also impossible for shell data to obtain a flux calibration where to derive, for instance, the H alpha flux and the mass. So here is the final product that produced Maria Teresa as for the jet, and we can see in the panels A and E that the jet indeed goes down to the central star. So we can confirm this, but the morphological description of the jet is not very complete. Now, integral field spectroscopic observations are becoming very important and very essential tool in our field, and particularly when there is high dispersion observation. These can be used to derive the 3D physical structure of the PN. So there is a large number of papers published on this topic, and we have 5 different tools here in this meeting. So we decided to use Megara, an integral field spectroscopic unit at the Grand Count telescope of the Canary Islands. And in particular, we use the VPH-665 grating, which is providing a very high resolution of 20,000. The integral field unit has 567 X-pixels with a size of 0.6 arcsecond. So it's a very good instrument, but the problem is that the field of view is very small, around 12 times 11 arcsecond, which is smaller than the size of NGC 2392. But we are stubborn, and we decided to map completely the nebula with 19 different pointings. And so actually the jet is mapped by 15 of these fields. And we have detected the jet, the emission in thousands of those X-pixels. So in this way, here is an example of one of those fields. We can distinguish, we can isolate the emission of the jet from that of the nebular emission. And we can produce images of the jet which are completely free from the emission of the nebula. The analysis of the spatial kinematic of the ring and the envelope is still in progress, but you can see here that there is a perfect match of the different components that we see in direct images and we see in our IFS observation. And so actually, when we are trying to cross-correlate the position of the different fields, we are very confident about this. So let's go to the main product that I'm presenting here, which is for the very first time, the image of the jet in the Eskimo Nebula. So we have the flux distribution in the nitrogen 2 and sulfur 2 lines. This was not possible for H alpha. because we can resolve H alpha perfectly in the what we call here the mid jet or the outer jet. But when we get into the inner jet, the expansion velocity of the rim is very high, and so there is confusion of the different kinematical components at this position. We also have the velocity here in the nitrogen 2 line, and we see that there is a clear gradient of velocity in this jet. We also have the velocity dispersion and even the density of the jet. So how do we relate to the PN? Well, first thing we notice is that the jet indeed emerges from the central star. It's not that we are looking at some preferential direction and that there's projection effect. So we see that the red and the blue components are at both sides of the central star. The jet then goes through the edge of the rim of the inner shell and it gets outside. So actually, if the jet is emerging from the central star right now, it goes across the main nebular shell and it gets out. And when we look at the right panel, we see actually that the jet even goes outside the nebular shell. So it goes all the way along the inner shell, the envelope, and even beyond those limits. And also we see that there is some kind of wobbling of the jet. So it's not completely linear, but it goes with some point symmetry from one side to the other.
2 minutes.
Okay, thank you. So we didn't see the jet here in the image, but actually, if we help our eye and we use the right filters, we can see that there was sun emission there, but actually it was impossible to distinguish from the nebular emission there. So because we see this wobbling of the jet, we could apply a simple model of the precession jet to try to fit the spatial kinematical components that we did here. So we have our fit, best fit with the thick line, variation of the parameters at the dotted lines, and we see that there is a good match of the observed properties of the jet with our model. So we can derive the jet properties, and here I would like to emphasize that the full linear size of the jet is 1 parsec, which is 2.3 times larger than the inner ring diameter. Sorry, that the whole nebula. We have an age of 2,400 years, which is about 4 times the age of the inner ring. Then we have a total ionized mass of 2.5 10 to the minus 4, and the mass loss rate and accretion rate, actually, they are in contrast with what we expect from the stellar mass loss, which is much weaker. It's lighter than what we see here. How do they compare with other sources that we have post-common envelope PN jets? Well, you can see here that the velocity of the jet is comparable. The ionized gas mass is of about the same order, or maybe a bit smaller. And as for the age, we see that in this case, the age and the ejection time scale is the same. So the jet is still active. When we compare this with the images of those systems, we see that there is a notable difference here. In all the jets that we see here, the jet is not connected to the central star. So there is those jets, they ceased their activity some time ago. We know that AGB stars, protoplanetary nebulae, young planetary nebulae, they are still collimating the jets, but NGC 2392 is the only mature PN where we see that the jet is being collimated at this moment. So what we consider here is that there are lots of resemblances between Fleming 1 and NGC 2392 that we are seeing at 2 different angles. Fleming 1 from a side view and NGC 2392 from top view. And actually there are different components here that can be interpreted very well if we consider these 2 different points of views. The envelope for the 2 PN, the jet that in the case of Fleming 1 sees some time ago is still active in NGC 2392, and also the low ionization features, the spokes and the flare in the 2392 that we can also see in the case of Fleming 1. And that's it. Thank you very much.
Thank you very much, Martin. Really, really nice data and really nice subject. So, yeah, questions for Martin?
I have one, but I don't know how to put my hand up.
Okay, go ahead, go ahead.
Okay, thank you. Excellent talk, Martin. Always enjoy hearing you talk. I'm interested in a few things here. First of all, when you look at the nebula previously known as the Eskimo, we could call that, it has no hint, as you said, in the N2 imagery that there's any kind of jet there. And it's only when you look at the San Pedro Martir kinematic shell data that you can see something that led to all this study. Now, how many cases are like that in the literature of the PN that look like this that we don't know there are jets because we don't have IFU coverage, we don't have SPM coverage in the right areas to pick something like this up? What is interesting to me is that in a bubble that we see there, you see that in some PN, but it's quite rare. This kind of bubbles that you see in the middle, that you often have X-ray gas filling those bubbles, as you've shown from your own work, and they look like this soccer ball structure. So some PN, you just see the soccer ball structure, nothing else outside. Others, you see this inner soccer ball structure inside another PN, a bit like the nebula previously known as the Eskimo. And so I'm just wondering, you know, how much more is out there to be found in this way? And I think you're right about that other object as well. Anyway, that was all. I was just a comment, really.
Yeah, actually, we see this kind of filamentary structure in some planetary nebulae. Toalá is very interested in those. So it seems that those shells, they are expanding at quite high velocity, and so there is some kind of, I would say, at some moment, the material in the shell is breaking with some instabilities and producing those filaments. As for the discovery of jets in sources where the jet is maybe pointing along the line of sight, Jacqueline Rechy-García is doing an excellent work. She has been using the San Pedro Martir catalog to discover a few sources where we see nothing in the images, but we see jet or fast velocity components in the PN. And now we are using also Megara, this tool, to unveil for the very first time those jets in those sources that she called bipolar, spectroscopic bipolar nebulae.
Okay, thank you. Lucero, go ahead with your question.
Thank you. Very nice work, Martin. It's amazing the results that these instruments can produce. I just have a question, maybe I got lost, but is there any evidence of the interaction of the jet with the inner bubbles that we've seen of the Eskimo Nebula?
Actually, I was thinking that that could be something very reasonable to find, to have the interaction between the jet and the inner shell. But you can see here that the jet itself does not stop at the edge of the ring. So the jet actually emerges from the inner shell. We are now investigating the kinematics of the inner shell to see whether there is any evidence of this interaction. So far, we have not found anything obvious there. And actually, if you look even at the dispersion of the velocity of the jet at this location, we don't see anything obvious. So the jet seems to go just through this shell, and the shell might be too tenuous to produce any effect on the jet.
Okay, thank you very much.
Ursula?
I am disturbed by something which I now know is in several other post-common envelope binaries. So first of all, the question, forgetting the jets, am I understanding right? So the Lion's Head Nebula, is that the way we're calling it now? Its geometry, aside from the jet, we're kind of looking down axis. Is that
Yes, this is the case.
Okay, so we are all agreeing that the jet is transverse.
Yeah,
the jet is kind of, let's call it 90 degrees.
Yeah, the jet is inclined by, well, the precession axis of the jet is inclined by 30 degrees with the line of sight, and the precession angle of aperture is about 6 degrees. So basically it's pointing toward us.
Okay, so there are 4 objects that I have here in front of me that have what I have always felt was, well, there's definitely a jet-like structure which looks transverse to what appears to be a ring or a spherical nebula. And not these. They're like, I have them here. Maybe in the discussion I can show them. So the thing is that's interesting, I've always been wondering why these jets are so sideways. And of course, precession may well explain that, but there's something, I wonder whether this is a commonality in the post-common envelope objects.
Well, you can see here in those cases, for instance.
And if so, that's good.
Yeah,
right?
I think the necklace, Fleming 1 and also Abel 63, you see that there is a kind of ring-like structure, I would say knotty ring-like structure there, which is quite orthogonal to the jet. And the jet is still there, it's wobbling, it's kind of precessing along this axis.
Right.
Yeah, of course, if those are on the plane of the sky, it's very easy for us to detect those jets. But if they are looking toward us, then it's much more difficult to really find what's the whole physical structure of the PN.
Yes, in this slide that you show, the one that's closest to, I think, the lion's head, and is NGC 6337, that once again as a ring, you're looking kind of down it, and you have something that's really sideways.
Yeah.
And I don't know if Noam has, of course, I'm sure Noam in your 97 paper, you've explained them all. There's bound to be something about these ones too, but it's extremely inclined, right? It's more so than, maybe if Brent was here, he might be able to say whether these are predictors of closed binarity. I also see a lot of filaments in 6337, which Brent has shown to be one of the things that can predict binarity.
Also, sorry, I did not understand your question. What angle disturbed you, between what and what?
The fact that you are usually looking at something that has a main axis sort of on the plane of the sky, such as a ring that is really the waist of something, and the jet is, let's say 90 degrees to be exaggerated, but the jet is transverse to that axis.
I mean, it's inclined by 30 degrees.
What 6337 looks like it's got.
No, it's
well, 30. Okay, fine. It doesn't have to be 90, but
we're looking on the torus, and you say the jet is 30. What Martin says is that the jet is 30 degrees to the axis of the torus or whatever. This would bother you? Lost connection with also.
Yeah, actually, the other point is that when you look at the properties of the binaries in these systems, they used to be also the orbital plane is transversal, is orthogonal to the direction of the jet, and is more or less confined to the plane where we have those ring-like features, which is consistent with a binary system and the jet being emitted along the orthogonal direction of the orbital plane.
So also what bothers you is that the axis of the torus or whatever shell, the axis symmetrical shell, is not aligned with the jet axis. I'm not sure what bothers you.
So it's particularly, is very non-aligned. It's particularly out of alignment.
But in most cases, it's aligned.
30 degrees is a lot.
Well, what is the alignment?
Well, in many it's not. I have 4 of them right here.
Well, maybe we can take a look at this, where we have the model that Maria Teresa obtained. So maybe it's not a question of the, I mean, 30 degrees with the line of sight could still be orthogonal to the ring, because the ring might be also inclined. So the envelope of the NGC 2 may be a bit inclined. I don't know whether Maria Teresa is listening to the talk now, but she made a very complete model of the nebula. So she can tell whether this ring with all those low ionization features is really on the plane of the sky or is tilted by some angle. Brain itself said that the orbital plane of the binary system in this nebula was inclined by something like 10 degrees. So things are getting closer. So it's not completely pulled on, but the system could be a bit misaligned with the plane of the sky.
But here also, if you look, you have this structure here with this axis. And here, if you look at this part of the jet, it's along this axis. So we see multipolar planetary nebulae. It's part of the binary interaction, I think.
Yeah,
rotation and so on.
May I intervene? That's a bit of a question. Let me turn the video back on. Yeah, we're assuming here that the jet is perpendicular to the accretion disk around the companion. But there is no real reason why that accretion disk has to be in the orbital plane, because you get spin-orbit coupling, and that this could change quite dramatically from that angle and could precess and do all kinds of funny things. Certainly in the Helix Nebula, there is also a jet, and everything points at a similar type of binary in there, but the jet is in no way aligned to the helical structure.
Yeah, to me, it's more important to try to understand in this system which star is accreting material from which star. So I think that there is maybe a white dwarf there which has nothing to be that we are not seeing in the optical, because it's very small, but it's very hot. And this is the one which is really accreting material from the central star of NGC 2392. And so actually the parameters of the stellar wind, velocity, mass loss that we see has nothing to do to what we see in the jet, which may imply that actually the stellar wind is not symmetric. And actually Prinja and Urbaneja, they pointed out this, that the stellar wind that we see from the central star of this nebula is variable and is not symmetric. So what we see is what we see along the line of sight, but maybe there is much more mass loss there, which is being redirected to an accretion disk around the companion. And that's something I think that there is a lot of physics there to try to understand. Why is this a post-AGB system, which is a mature PM, but still there is accretion and collimation of the jet in this system?
So it's a symbiotic. If the white dwarf companion ionizes the nebula, then it's symbiotic.
Yeah, but it's a white dwarf companion, and the center star is also white dwarf. Is at least post-AGB star evolving into the white dwarf stage. So I think this is the right situation of the system now, but I think we need more evidence for this.
Could it be a disk wind?
Sorry, a disk?
A disk wind.
What is the difference between a disk wind and a jet?
It comes over. It's a wider angle outflow.
Okay, what the angle change from? When do you change from jet to what?
Well, it depends on the launching mechanism. If it's a jet, is it? If it's a magnetic tower, yes, then it's quite a separate structure. Even in a disk wind, you get more of an X wind.
Yeah, as far as I can say, the jet is not very collimated. You see that the jet, the outflow that we see here is quite wide. It does not compare very well, for instance, with what we see in Fleming 1, but it could also be a question of projection effects. I mean, if you are looking at the jet of Fleming 1 from the top of the jet, maybe all different components are merging there, so you don't see this filament, but something which is just moving at the same speed, and so you are not able to resolve it properly. So it might be that this is not that much collimated jet, but I think it's not possible right now to claim that, because projection effects could be very important.
Jesus comments that a magnetic field is not seen. You would have detected in the X-rays.
No, no magnetic fields here. And actually, at some moment in 2005, I made a claim that the X-ray emission was aligned with the jet, but then with much better resolution Chandra images, we see that there is no correlation in the spatial distribution of the X-ray with the jet. So apparently, there is not such correlation. So in this sense, as Lucero was asking, there is no great evidence of the interaction between the jet and the inner ring, so the innermost shell, which should be confined in the jet, but it is not, and there is no evidence for shocks or whatsoever.
There is some activity also going on the chat. Miguel, Jesus, Carlos, you want to speak up?
Sure. Well, in my case, it's just a comment that if there's a disk that is responsible for the jet, if it's still there, couldn't we detect it somehow?
Well, not in the near infrared or even infrared observation. I think this star is very, very bright, and there is no evidence for any infrared excess. So we might need to be looking at different wavelengths to see this.
That would be very interesting to do.
Yeah, indeed, indeed.
Vincent wants to say something.
Mute, come on. Yes, hi. If the disk does launch a jet, then just physically speaking, the physical conditions at the foot point of the jet should be practically identical to the physical conditions of the surface of the disk. And therefore, I think the answer is yes, to Miguel, right? I mean, you should be able to detect the surface of the disk as well as detecting the foot point of the jet. So the only possibility for not having that is that if what we see in the image on the screen here, the foot point of the jet is somehow not observed, but I have no idea why that would be.
Carmen, may I say something about detecting the accretion disk?
Sure, go ahead.
So, you know, a characteristic signature of accretion disk is flickering. So a possibility is choose the wavelength at which the object is, or the central star is brightest, and carry on do a light curve of that with high temporal resolution and look for flickering.
Yeah, the question is that the stellar wind itself is variable in this case. And I know that there are some claims in the literature of variations in the magnitude of the star, but these need to be looked very carefully because the star itself has a variable stellar wind. So that's something that needs to be really addressed very carefully. We are trying to obtain high dispersion observation with a time resolution adequate for this. And maybe in the near future, I may have some more, I don't know whether answer, but maybe more questions about it.
The flickering would be on generally very short timescales. I think probably shorter than the wind itself, unless I mean, it depends what part of the wind you're talking about.
Yeah.
The wind, which is at as Vincent said, anchored at the footprint of the footprint of the wind on the accretion disk. That's presumably the region where the flickering is taking place, where the accretion is happening, right? So,
yeah,
but it'd be worth. It's a good experiment to try.
Definitely.
Okay, good. We had a very nice discussion on this one. So probably we can just move now to the next talk.